Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And I think you have a bunch of questions here. All right, let's start off with one from D96. When an electron moves from one energy level to another and releases a photon, is the direction of the photon random? Okay, so let's explain roughly what's going on there. So in an atom, there's a nucleus that's made of protons that have positive charge and neutrons that have zero charge. And then there are electrons that are kind of going around the nucleus. The nucleus, the electrons, the nucleus is quite small. The average distance that the electrons are is like 100,000 times the size of the nucleus. But there's this kind of cloud of electrons around the nucleus. And the way that one describes how those electrons sort of exist around the nucleus uses quantum mechanics. And in fact, in our new theory of fundamental physics, we're sort of slowly getting to the point where there may be a very much easier way to describe what's going on with those electrons. But roughly what's happening is, normally one might think, oh, there's something that's orbiting something else. There's an electron that has negative charge, so it's attracted to the protons which have positive charge in the nucleus. The thing is just going around, and it's swinging around like a satellite would go around the Earth, being sort of kept in orbit by, in the case of the satellite around the Earth, by gravity. In the case of the electron going around the nucleus, by electric forces. So that would be kind of the classical physics picture of what's going on. In quantum mechanics, the key thing is that there isn't a definite trajectory that things move along. Instead, things, in a sense, move along all possible trajectories. And there's a certain likelihood that they follow each particular trajectory. And we don't kind of get to know what that likelihood is until we make specific measurements and so on. And there's a whole elaborate theory of quantum mechanics, which I think we are managing to understand a lot more clearly. It's a fascinating subject, but let me not divert into talking about that. But one feature of quantum mechanics is that it tells one that electrons, as they go around the nucleus, can exist only have only particular amounts of energy. So when something is in orbit, let's say a satellite is in orbit around the Earth, it has a certain amount of energy, kinetic energy associated with motion that it gets from the fact that it's moving around the Earth. And the amount of kinetic energy that it has is, in that case, just proportional to the square of the velocity of the thing going around its orbit. And if you have a satellite in orbit around the Earth, the satellite can have, depends on the elevation of the orbit, affects the kinetic energy, but basically you can have a satellite with any possible value of kinetic energy orbiting the Earth, well, up to some limit, but at which point it will escape from the Earth. But actually a little bit, there's some trickiness there, but basically you can have you can have it have any kinetic energy you want. Just like if you take something and it's on a string and you're whirling it around with your hand, up to the point where the string breaks or some other crazy thing happens, you can make it go more slowly, you can make it go faster. That's the usual way things work in classical mechanics. In quantum mechanics, it works differently, and there are only a discrete quantized set of energy levels that are possible. And there are a variety of ways to understand why that happens. Roughly, the typical way that uses the standard mathematical formalism of quantum mechanics uses a thing called the Schrödinger equation. And basically what happens is that the description of electrons in an atom are described by a so-called wave function. And that wave function has the feature that it kind of is, its values are a little bit like the displacement of a string that would be sort of plucked. So for example, if we have a string and it's attached at its two ends and you pluck it in the middle, then one possibility is the string just goes up and comes down again. Mathematically, it would be, sine pi x or something. The other possibility is that the string has sort of two maxima. So it goes up and down and up again. So that would be mathematically sine 2 pi x or something like that. And in general, you can have a string that has any number of those maxima, sine 3 pi x, etc., sine 4 pi x. Those, when we look at the frequency with which the string is vibrating, that will go up. In the case of a sort of ideal string, that will go up by integer amounts. So it'll be either the fundamental frequency or frequency times 2, times 3, times 4, times 5, etc. Okay, so when you have the string, its kind of possible frequencies are quantized. That's just a feature of the fact that it can have 1 wiggle, 2 wiggle, 3 wiggles. It can't have 2.5 wiggles, because that wouldn't end it up with something where it will be sort of attached at its two ends. It would have half a wiggle that sort of overshoots the attachment point at the end. So it has to be quantized into a fixed number of wiggles. Okay, so in quantum mechanics, through Schrödinger's equation, through this wave function idea, the same thing happens with electrons. Their wave functions have to be kind of arranged so that they kind of, within the size of the atom in some sense, they can only wiggle a fixed number of times. And so what that means is, in the case of electrons, the frequency of the wiggles on the string translates into the energy of the electron. And so what that means is that there are discrete energy levels for the electron in the atom. So again, whirling something around on a string or having a satellite orbit the Earth, there aren't a fixed discrete set of energy levels. There can be any energy you want. But in an atom, the electrons can have only a fixed set of possible energy levels. Okay, so if you heat up an atom by literally putting it in, having it be bouncing around with hitting other molecules, hitting other atoms and so on, as you would when you literally heat it up, increase its temperature. One of the things that can happen then is that the electrons in the atom can get pushed into higher energy levels, excited states. But then those excited states, again, as a result of quantum mechanics, and this now requires, to do it properly, requires so-called quantum electrodynamics, quantum field theory, but you can sort of approximate it with sort of ordinary quantum mechanics. There's a certain probability that that electron that's in its excited state will emit a photon and go to a lower state. So always these are discrete states. So for example, in the simple case of a hydrogen atom, there's just one proton at the nucleus and one electron kind of in orbit, so to speak. In the first approximation, the energy levels of the hydrogen atom go like some constant minus, 1 over n squared. So the nth level, that determines, that's the kind of mathematical formula which determines where the energy levels are. As it gets to the point where you put so much energy into the electron, eventually the electron will escape the nucleus. And at that point, the 1 over n squared, the n gets very big, the levels get very, very close together. And that's kind of a representation of where you're about to hit so-called ionization, where the electron will escape from the nucleus. But normally, there are these energy levels that are separate, that are defined by these just mathematical numbers, and they're discrete energy levels. Okay, so then the photons that get emitted are emitted by transitions from one energy level to another. So in the case of hydrogen, there are famous named transitions, like the so-called Lyman alpha lines. Those correspond to photons that are being emitted when they make a transition from one particular energy level to another particular energy level. You emit, in that case, ultraviolet photons that are important for astronomy in that case. But every for hydrogen, because it's sort of a famous element, some of those things are actually named. But in general, what's happening is you're making a transition from one quantized energy level to another. And so if you have lots of different energy levels, there might be many different transitions that can be made from one energy level to another, from another one to another. There are lots of different energies of photons that can be emitted. Okay, so when this emission happens, so you've made the electron go to this excited state, it is going to decay down and emit a photon to go to a different state, maybe to the lowest state, the ground state perhaps, or maybe to some other excited state, but it's going to emit a photon. Okay, so the question that was asked was, when it emits a photon, when it spontaneously emits a photon, that's spontaneous emission of photons. That's when you have a laser, there's stimulated emission of radiation. That's not spontaneous emission. It works in a different way. But when you have an ordinary atom that's been sort of thermally excited by just increasing its temperature, the emission of photons is this spontaneous emission of photons. And there's a certain, depending on exactly the details of the atom, there'll be a certain rate at which that emission occurs. Okay, photon is emitted. Where does the photon go? Well, so just as the question of when the photon will be emitted is random, but follows a distribution, it follows an exponential decay law. So similarly, the direction that the photon is going to be emitted is also random. But it's a little trickier than that because, and this is where, gosh, if I can explain this, I'll be pleased with myself. Okay, it turns out that it depends on which energy level of the electron and it's starting from, and which energy level it's ending up with. That affects the angular distribution, what direction the photon, what the distribution of directions that the photon will go in is. Now, again, oh boy, this gets more and more complicated. Okay, so you have an atom, and you might say, well, the atom is just like spherically symmetric. It's like any direction. You can rotate the atom any way, and there's no real difference between different sides of the atom. But that's not always true, because an atom can be spinning on its axis, and it can have an angular momentum that's spinning around, like the Earth spins on its axis, and it has sort of a definite, in the case of the Earth, it has sort of a definite pole, and you know where it's spinning around. In the case of atoms, quantum mechanics says it's a little bit more subtle than that, but there can be this notion of so-called quantized angular momentum. So just like the energy levels are quantized, so also the angular momentum is quantized. So it can have 0 units of angular momentum, half a unit, 1 unit. It happens to go in half units, okay? So it can have, let's just say 0 unit, 1 unit. Actually, for these purposes, for the purposes I'm now describing, 1 unit is right. The half unit has to do with what happens with electrons specifically. But so it can have 0 units of angular momentum. It's actually, the units that are used are units of Planck's constant over 2 pi, but that's irrelevant. So h bar is the name of that thing. So it's kind of 0 h bar units of angular momentum, 1 h bar, 2 h bar, and so on. Okay, so essentially what's happening is, as it gets more angular momentum, it's as if the thing is spinning on its axis faster and faster. That's not really quite how it works. Quantum mechanics has a slightly more subtle thing that goes on to represent this kind of angular momentum. But as soon as you have angular momentum, you have an axis defined. You have, there's a north pole, there's a definite direction, so to speak. And then you can start asking, is when a photon is emitted, where is that photon going relative to the direction of that angular momentum? And so what happens is there are some photons that are emitted where they just don't care about the direction of angular momentum. And there's some photons emitted where they will care about the direction. And in particular, there is, as you get higher and higher angular momenta, there will in a sense be more and more possibility of caring about which direction you're going in. Because roughly what happens is, as you get, and I'm going to make another math formula here, as you get angular momentum J, the number of different possible states of the atom is 2J plus 1. And that means that in some sense, there are sort of more different possible ways in which the photon can be emitted. And so it cares more about the specific direction it's emitted in. Now, it turns out, as you look at these sort of, as you say, consider higher angular momenta, the different sort of the angular distribution, when the angular momentum is 0, the angular distribution is like, I don't care which direction I'm going in. It's equally probable that the photon goes in all directions. When the angular momentum is, let's say the next level up is, I think it's 3 cosine squared theta minus 1, if I remember correctly, is the next. So basically what happens is oh gosh, this is I'm it gets kind of complicated kind of quickly. But let me say a little bit more mathematically, because it might be interesting to people. If you know about sines and cosines, they are they represent kind of, if you are looking at things around a circle, if you're saying I have this density at different points around a circle, you can always represent that as, well, you've got this amount of sine theta stuff, this amount of sine 2 theta stuff, sine 3 theta, and so on. The corresponding thing for 3 dimensions on a sphere are things called spherical harmonics. And the distribution of intensities of photons at a given, with atoms with a given angular momentum is determined by these spherical harmonics. And as you go to higher momenta, higher angular momenta, the spherical harmonics that correspond to the angular distribution of photons get more and more peaked around different directions. So that's more or less how it works. So the answer in the end is the distribution depends on the spin of the angular momentum of the atom, and things about the angular momentum associated with these different energy levels, and that will determine whether the thing is uniformly distributed or whether it has a distribution which somehow follows the direction of the sort of the axis of angular momentum for the atom. So that's basically how it works. So I'll tell you one little extra piece of sort of trivia in a sense about emission of things from atoms. So you can look at things like photon emission for an atom, but when you have radioactive decay, you can have other kinds of emission from at least the nucleus. So a famous kind of radioactive decay is beta decay. So in beta decay, the nucleus, what happens is basically roughly a neutron in the nucleus decays into a proton, an electron, and an antineutrino. Okay, and so what you'll actually see is the nucleus will sort of self-destruct with one of its particles transmuting into something different, and an electron will be emitted, and a neutrino, which is this very light, very hard to detect particle, will also be emitted, and so the electron will come out in one direction and the neutrino will come out in basically the opposite direction, just to conserve momentum. Okay, so one of the big questions was sort of a basic question about the universe is the universe what's called parity invariant? So that means if you take a picture of something that's happening in the universe, you say, this is a valid picture of something that happened. These particles collided, they did this, they did that. And then somebody says, let's invert that picture. Let's just essentially reflect it in a mirror. Let's just switch around all the directions. So everything that was going one direction now goes in the exact opposite direction. Okay, is that after you make that parity transformation, can you tell whether the image that you had is still a valid image that could exist in our universe? In other words, is the universe invariant under space inversion or parity transformation? Is this picture, you could say, no, that's wrong, that couldn't possibly happen in our universe? Or is it the case that if one version of it worked, then the version where everything was inverted would also work? So back before, well, I'm kind of when quantum mechanics was first being developed, people thought the universe is invariant under parity transformations. So in the 1930s, 1940s, if you ask somebody, does the universe have the symmetry that every process is invariant under parity inversion, they would say, yep, that's the case. Okay, until 1956. In 1956, an experiment was done on beta decay, which discovered that the universe is not invariant under parity inversion. And the way that experiment was done was, in this case, the atomic nucleus had an angular momentum. And then the question was, is the angular distribution of emission of electrons invariant under inverting the direction of angular momentum? I didn't really explain why this is the case, but it's the case that is a condition for this parity inversion working, is that the angular distribution should not care whether the axis is pointing sort of up or down. It should be the distribution of directions that electrons should go on should be symmetric under being aligned with the axis or anti-aligned with the axis. Okay, so in 1956, some people, I think in New York, did this experiment on, oh, I can't remember, what is it? Which element? Memory failed on that one. But anyway, on a radioactive decay, beta decay, and they discovered that no, actually, it wasn't symmetric under inversion up and down. So that proved that the universe is not invariant under parity inversion. And why was that? How do we sort of understand that now? Well, the reason we understand that now is because neutrinos, which have an angular momentum, they have a spin. The reason that we can see this is basically all neutrinos are pretty close to exactly left-handed. That is, the direction, if the neutrino is going in some direction, the spin of the neutrino is always aligned so that it's kind of curling around like the fingers on one's left hand and not like the fingers on one's right hand. So the neutrino kind of knows that the neutrino is fundamentally not invariant under parity inversion. And okay, things get a little bit more subtle. The antineutrino is then right-handed, and then there's another level of this kind of question about invariance under inversion. And while the universe was known in 1956 not to be invariant under parity inversion, people thought that it was still invariant under a combination of parity inversion and so-called charge conjugation, where you take the neutrino and you make it into an antineutrino. You make every particle to its antiparticle, and you do the spaced inversion. People thought that was still a symmetry of the universe until 1964, when it was discovered in the somewhat obscure in the decay of the K0 meson. It was discovered that, in fact, there was a violation of CP invariance, of combined charge conjugation and parity invariance. And so then that was known not to be a symmetry of the universe. But then the one surviving symmetry is so-called CPT invariance, which is the combined invariance under charge conjugation, space inversion, and time reversal. And that invariance is pretty much guaranteed by theory of relativity. And if it isn't true, then all kinds of funky things happen. Now, an interesting question is whether it's true in our fundamental theory of physics, whether it's true at extremely small scales in the universe. And the answer is it will not be exactly true. It will be something that is only true when we get to very large scales. It's something that will be that's only that emerges as true when you look at a large scale. But if you look at sufficiently small scales, if you look right down at the level where you can see that space is discrete, it will no longer be true. So there's sort of some interesting things there. And actually, it occurs to me that I'm about to work on a bunch of things to do with the experimental consequences of our models of physics. And I should actually look at the whether CPT in violation can be amplified around particularly spinning black holes, which might happen in our models. Okay, note to self that I should look at that. So thanks for asking that question, because it led me to this. Okay, let's see. So that was a very long answer to this question from D96 about direction of photons random. See, these things get kind of complicated. I mean, if you want to know, perhaps it's interesting for people to know sort of the official, no, maybe not. I mean, I could tell you sort of the official lingo of of how you'd answer that question, but I don't think perhaps I think I gave you the basic description here. Okay, let's see. I see is asking, how do you remember all those formulas? The formula I was quoting actually is those are Legendre polynomials, and I think I remember the first two Legendre polynomials. Those are, yeah. Let's see. There are some questions here. Oh, there's a question from Setor. Can you explain inertial versus non-inertial reference frames? Okay. So let's first of all set some kind of, the real question is, if you are in an elevator, for example, or if you're in a closed box, and you're just doing things in that closed box. You're doing a bunch of physics experiments. You're doing this, you're doing that. The question is, closed box, you can't see outside. And the question is, if that box is traveling at a high rate of speed in some direction, can you tell? In other words, in the closed box, can you tell what, if you're just going at a certain speed without any acceleration, you're just, you're freely moving at a certain speed, can you tell what speed you're moving at? So Einstein's special theory of relativity, its big point is you can't tell. But you only can't tell if there is no, if you're in so-called inertial motion. If you're in, if it's just, so, okay. So Newton's first law says a body that is put in motion will stay in the same state of motion unless it's acted on by an external force. Now, there's some sleight of hand in the way that that definition is made, because it's sort of a definition of force, and it's not clear what it really sort of says. But what it means operationally is, if you're, forget the Earth, forget having gravity where things fall, forget all those kinds of things. Imagine you're out in space between the galaxies. There's essentially no gravity from anything. Well, there'll always be some gravity, but essentially there are no sort of gravitational effects, and you're out in intergalactic space and you throw a ball. Well, and it's in a vacuum and everything. The ball will just keep going in a straight line. It will just, that is what Newton's first law says, and that's what will happen. Now that's what's usually called inertial motion. It's moving just according to its inertia. It's not acted on by some external force. Now, if you threw the ball near the surface of the Earth, we know, ignore air resistance and all that kind of thing, the ball will fall down because of the effect of gravity from the Earth. Okay, so similarly, you're in your closed box and you're asking the question, am I near the Earth or am I in intergalactic space? Well, you can tell if you're near the Earth or if you're in intergalactic space, because the ball will, if you're near the Earth, the ball will fall down in some direction associated with the gravity of the Earth. If you're in intergalactic space, the ball will just sit there and will not fall. So the concept of an inertial frame and inertial motion is the concept of, if you're in a place where there's sort of no forces acting, and you're just moving in the way that inertia would have you move, then that's what corresponds to an inertial frame. Now, you can get an inertial frame even when you have when you have gravity there. If you're in free fall, like you're in an elevator and the elevator is just, if you know, that's a bad scenario for an elevator, but if your box is just freely falling in the gravity of the Earth, then you also are in this inertial state where you are not. That maybe is a confusing case, so forget that case for now. Let's consider the case where you just no forces acting on you. Then you kind of you can't tell what speed you're going at. Everything will work the same. If you are in a so then the sort of second level of things that leads to general relativity is associated with this so-called principle of equivalence, which says that there are, when things fall, if you drop your ball, if you in your box and the ball falls, why is the ball falling? Well, there are two possible explanations. One is you're in a gravitational field, and the other is that your box is accelerating in some direction. And so the principle of equivalence is about essentially the equivalence between sort of being in a gravitational field and having this acceleration imposed on you. And so the idea of a non-inertial frame is something where there is something like a gravitational field that's associated with your that's there, or alternatively that there's some acceleration, some force that is pushing you to change your state of motion. So things, needless to say, get unbelievably much more subtle than this. The whole question of what it means to be in a certain state of motion and so on depends on how you're measuring. What is motion? Motion is you're changing your position in space as a function of time. But what is your position in space? Well, you have to be able to mark off different points in space. So let's say you have a meter rule, physical, hard meter rule. You can say you're moving from one place on the meter rule to another. That's all easy to understand. But let's say there is no meter rule. Let's say that you are defining points in space by some procedure. Let's say you have light signals bouncing back and forth, and you're using that to sort of virtually create a meter rule. Well, things get extremely much more subtle when you do things like that. And typically what happens is people initially start thinking about, well, in these situations where there's a gravitational field, for example, the gravitational field of a black hole in an extreme case, which is a strong gravitational field, there is there's sort of this question of what counts as different places in space, and how do you put down coordinates that represent what's going on in space, what the different places in space are. It's extremely subtle, and in fact confused people from about 1915 up until pretty much the 1960s, how you would put down those coordinates for something where you had a strong gravitational field. So that, and this question about what kind of non-inertial frame you're in, and what counts as motion and what counts as gravitational field and so on, very subtle kinds of issues that eventually get untangled. They're actually somewhat clearer in our model of fundamental physics, but to explain that I kind of have to go and start talking about sort of the discrete structure that lies underneath space-time, and that gets us off in a whole different direction. But in our theories of physics, the notion, let me not go here. I can talk about inertial versus non-inertial frames there, but I mean, I can say the words. It all has to do with anti-chains in partially ordered sets that correspond to the causal graphs of evolution in our models. But I can unpack that, but that will take me a solid 15 minutes to unpack, and I want to try and get on to some other questions. So maybe another time I can talk about that. Let's see. There's a question from Amorita. Why do humans have an appendix even though it is unnecessary? So what is the appendix? Inside our intestines, there's this kind of dead end where there's sort of a pocket of intestines, and unfortunately things sometimes get stuck there, and then you get appendicitis, and you get infection there and so on, and that's a bad thing. And when you have surgery for appendicitis, you just sort of snip off that part of the intestine and make it a smooth bend rather than something that has a little pocket in it. And it seems like it doesn't do anybody any harm to do that. And it seems like, why would there be that weird pocket where stuff can get stuck and get infected? Just seems like a bad idea. So how do things like that happen in biology? So there are two branches to the answer to that question. One branch is, you say it's unnecessary, but has it really always been unnecessary? That's branch number one. And branch number two is, the way that biological organisms get designed is not by a process of kind of people thinking about the design, at least not yet. It's more a process of biological evolution where random changes get made. And if one form of the organism is more successful than another and has more progeny, more children than the other, then it will be the one that wins out. Okay, so let's first of all take the branch of, is it really unnecessary? Okay, so one of the things that happens rather often in biology is people say, oh, I don't know what that does. It must be unnecessary. So for example, people said that about large parts of the brain. People said that about large parts of the genome. We don't know what it does. It seems unnecessary. The part of the function of that thing that we understand, 90% of the thing doesn't contribute to that function, so it seems unnecessary. So, when it comes to, now, is that really right? Well, a couple of reasons why it might not be right. One is you might just have not understood what that other 90% does. It might be something where, like in the case of the genome, it might be something that's important for kind of the structure of the way that the molecules actually organize themselves and which parts get activated and which parts are close to each other. And these things that seem like they're unnecessary because they're not relevant to actually, let's say, making proteins, which is the function that we initially know that the genome is performing. They're not necessary for that, but they are necessary for something we didn't yet understand. So the first thing is, when we say it's unnecessary, we might be wrong. Now, the second thing is, unnecessary now is different from unnecessary throughout the history of our species. So, for example, now, if you live in sort of some sort of fancy place, it's pretty unlikely you will get parasites in your gut. It's pretty, you eat food that's been passed by, food inspectors and all this kind of thing. You're very unlikely, unless something bad happens, you're very unlikely to end up with parasites. Now, if you live in a place where that isn't what's going on, I visited some such places. I've managed to get infected, not with parasites, but with other kinds of things from food. It's very common for one to have in many countries in the world. It's common for people to end up with parasites in their gut. Now, in a sense, that sounds very scary, but in some sense, it shouldn't be scary, because in our gut, there are many bacteria that live in our gut, and that's the normal way that things work. The bacteria are doing things that are useful to us. We all have a so-called microbiome that consists of populations of all kinds of bacteria, and depending on exactly what kind of food you eat, you'll increase or decrease the number of some kind of bacterium, and so on. Different people will have different microbiomes. If you take antibiotics, you zap out a whole bunch of those bacteria, because antibiotics attack bacteria, and that may be something which will put your microbiome out of whack for months. And sometimes your microbiome can be in some state where some particular species of bacteria has won out. So in some sense, those bacteria are like parasites living in our gut, except that they're pretty good for us, and they're important for the way that we digest food and so on, and probably for other functions too. But usually when we talk about parasites, it's protozoa, not I think usually things like amoebas and so on, not bacteria. Although you can get infected with bacteria in your gut, where it's bacteria that aren't the kind of bacteria that sort of should be in your microbiome, but they're things which are a sort of a foreign bacteria, and that's a bad thing. And you can end up with so anyway, the point is there's all kinds of stuff that if you're in a fancy place where there are food inspectors making sure there aren't any sort of parasites in your food, you'll end up with a microbiome with lots of bacteria in your gut, but not presumably protozoa and things like that. And in that environment, well, seems like the appendix doesn't have any important consequence. I don't know for sure whether in some scenario where there was some particular kind of weird, parasite, maybe the appendix is important in that case. Maybe it's something which, no, it's not important if you live in a place with food inspectors, but it is important if you're living in a place where you could easily get those kinds of parasites. So to say not important is something which may be a feature of just the last, 100 years of, food inspected places in the world, so to speak. So that's one branch of, is it really necessary, and so on. It may be that, it isn't necessary to you because of the way you live, but it would be necessary if you lived in a place where the sort of the diet and sanitation and so on was very different. I don't know that to be the case for the appendix. I don't think it necessarily is, but it's something where, that's something which is always a thing you have to think about is, was this useful? Even if it wasn't useful today, was it useful 10,000 years ago in the history of our species? Because we haven't evolved that far from over the last 10,000 years. Okay, so the second issue is maybe it is that way because when the organism grows, the gut is being formed in a certain way, and it's twisting itself up in some ways, and that's just left over as kind of a construction artifact. That is, it's like when you build a certain kind of building, you may have to, in order to get something on the roof of that building, you may have to build some whole scaffolding. And it's like, well, you could just take the scaffolding down, get rid of it, but maybe you'll leave the scaffolding up. And if you leave the scaffolding up, then you say, what's the use of that scaffolding? After all I care about is what's at the top of the building. But that scaffolding was needed to be able to get the thing to the top of the building. So there are some things that we have that are a consequence of sort of how we grew. I mean, there are things where you could say, well, I don't really, that part of what is there was sort of just a construction artifact. I mean, there are weird cases where, for example, for us humans, our fingers actually grow in a weird way. Initially we get the sort of web in utero, so to speak. There's the hand is just the sort of webbed thing, and then actually the cells that are in between the fingers die off. And so essentially there was scaffolding, which was the whole sort of web, and then a piece of the scaffolding died off, and that's what led us to our separate fingers. But there are places where that isn't the case. Another thing that can happen is, even independent of the growth of an individual organism, it can be the case that that biological evolution ends up going in a certain direction, and even though there might be a better solution, it can't get there from here. So a classic example of that for us humans is in our eyes. In the retina of our eyes, there are sort of light-sensitive cells on the back of our retina, and there are also some cells that make connections that start doing some of the basic image processing that our eyes use. And we really goofed up because those cross connections are in front of the photosensitive cells in our retina. And so it's like, that's a dumb idea, because the photons, the light that's trying to get to our retina, has to go through that level of cross connections before it gets to the light sensitive cells. It seems like a bad way to do it. Why did we get an eye that was built that way? Well, because the eye has evolved separately in several different places. There are critters, I think the king crabs, I think, have this. Their eyes sort of separately evolved, and they got it the right way around. They have it so that the cross connections are behind the photosynthesis cells. But if you look at the sort of tree of life evolving towards us, it's like that flip around is really hard to do. In other words, an organism which says, oh, well, I'm just going to drop out those nerve cells, I'm not even going to have them at all, it's probably not going to be such a successful organism. Its line will die out long before it got to the sort of full flip around version. So in other words, another thing that can happen is, not only can you not be able to get there in the growth of an individual organism, it can be the case that biological evolution just doesn't have a good way to get to that kind of optimal condition. And so that's how you can end up with these things that seem like they don't make sense, but they do make sense given the history of how you had to get there with biological evolution, because biological evolution can typically only make small changes. It's kind of, if biological evolution suddenly says, let's make a human that has two heads, well, there's probably a lot else you have to worry about. As soon as you have a two-headed human, there's a lot of issues that have to go along with being two-headed that have to be taken care of. And just saying it's two-headed, it's probably not going to work very well. So you can't make that sort of big change. You have to incrementally make the change, bud out the little tiny, subhead, and then slowly over the course of 10,000, 100,000 generations, it gets bigger, and et cetera, et cetera, et cetera. And eventually you might end up with the two-headed organism, so to speak. But it's not going to happen suddenly. And that's a characteristic of biological evolution. The way you can think about it in terms of other kinds of things is, imagine that you're trying to find the best solution to some mathematical problem. You've got the best solution. You're trying to say, what's the lowest point in this landscape, let's say, and you're trying to find that by sort of moving around the landscape. You're sort of probing around the landscape. In biological evolution, it's as if at every time a new organism with little random mutations is created, it's moving a small distance randomly on this landscape. And the question is, if you keep doing that, and you keep saying, well, I'm gonna be a winner if I find a little bit closer to, further down on the landscape, can you, by sort of randomly moving around like that, can you find the absolute minimum of the landscape? Well, you might not. You might be stuck in this crater over here, where you say, well, this seems like the lowest point because I move around randomly. I can't get to a lower point. I'd have to go and walk all the way over this hill, which I'm not to get to this even lower point over here. And that's just not something that evolution can do, because if it makes just those small changes to keep an organism that's still pretty fit around, it's never going to get to that more global minimum, so to speak. And so that's why you end up with these things that are sort of strange artifacts of the history of life. Okay. Okay, there are comments, apparently people saying that the appendix, apparently its use is storing good bacteria that help repopulate when needed. Okay, that's interesting. I mean, sometimes it's a challenge because sometimes you take you just take it for granted that biological evolution knows best. It's going to do the right thing. And if you see a phenomenon in biological evolution, then there has to be a reason for it. And so sometimes that can lead to very weird conclusions, because like, let's find a reason. What can it possibly be? Why do we have, I don't know, what's a good example? I don't know. Why do, why do we have the folds in our ears, for example? There has to be a good reason. I don't know, in that particular case. I mean, the whole shape of our ear, the whole pinna of our sort of outer ear is, that's useful because apparently, because it affects the way that sound is brought into our ears, and that helps us distinguish things like, is the sound coming from in front of us or behind us? But the exact, details of how sort of the ear is folded up the way it is, and the great diversity of those folds between different people, you might say, well, nature knows best, evolution knows best. There's got to be a good reason for that. There's got to be a good reason for the folding in the ear. Maybe there is. Maybe it's a consequence of the fact that it's easier to grow ears that way. I mean, in a sense, when you do technology, there's this kind of idea of design for manufacturability. I mean, back in the day, people would say, I've got this great design. I'm going to make this thing, and it's going to have this little robot, and it's going to have all these arms. It's going to do this and this and this. And somebody would specify, this is the robot that I want. And then it would be given to somebody, at the factory that was going to make the robot. And they say, what do you mean? How am I supposed to make this thing? How do I get it? There's no mold I can make that will make this thing. And how do I assemble it? And, how do I get that little piece in the middle sort of attached properly, and so on. And so then there was this kind of methodology that developed called design for manufacturability, where people thought about how you're actually going to make it. And biology, in a sense, is forced to do design for manufacturability because we grow. And there has to be a way to get to the way we are by biological growth. And so that's a thing that can affect the things you see, as I was mentioning before. And so, that's what biology did. It's got to be good for something. Well, it might be in some sense just that way because it grows that way, or it might be that way just because of the particular history of biology. Now sometimes you wonder about whether some detail, some big feature of biology today might be the consequence of some bizarre accident that happened 1 billion years ago. Like, for example, the fact that we have 5 fingers, not 6, not 7. The fact that there are lots of flowers and other organisms that have 5-fold symmetry. Why 5? Why not 6? Why not 7? Maybe that's because, well, 5 is better. It's the optimal point in some whole elaborate thing about, getting food and grasping things and all that kind of stuff. Or maybe could have been 5, it could have been 7, but some terrible misfortune happened to that strange little creature that might have been, embedded in the Burgess Shale from the Precambrian or something, that that some terrible misfortune happened to the 7 symmetry line of creatures. They just got, there was some, some volcano that, sort of wiped them all out. And it's purely a matter of historical chance that we've ended up with the 5 symmetry things. So there may be things like that. We don't know what things like that might exist in the history of biological evolution. I mean, we kind of expect that, the asteroid impact that wiped out the dinosaurs, that was kind of an external historical accident, and the consequences of that, might be things that were an example of this. I mean, the fact that reptiles are not the dominant form of life on Earth, maybe if it hadn't been for that asteroid, it would be kind of, if I'd been talking to you here, it would have been, as a stegosaurus or something. I think actually the days of the dinosaurs, people tend to think, was sort of numbered, even independent of the asteroid impact. But that's a separate issue. Parmenides is saying tailbones. Yeah, that's a good example of something which I think is that way because of the way things grow. And it's also, I mean, again, it's so hard to tell. It's like, you look at a whale, and whales presumably evolved from things that walked on land. And it's got some skeletal structure, and some of that skeletal structure is probably a consequence of the history of that, and so on. And maybe there are things that we have because we used to hang in trees a lot. Most of us don't these days. Lots and lots of details like that are historical features. Now, it's always interesting to see in terms of evolution. Biology is not the only place where evolution is seen. It's also seen in technology. And you can ask questions about, is the technology that we see the consequence of some strange path of historical evolution? Is the fact that, well, very, very obviously and simply the fact that we have a picture of a trash can as our, no, that's a bad example. The save icon, for example, that's a classic example. I hope there are enough people who are young enough on this live stream that the save icon might seem weird to you. The save icon that people often use is this picture of a square thing with a little side indent type thing. What is that icon? Maybe actually I haven't seen them so often recently, but I'm sure they still exist. The save icon, what on earth is that? Well, that's a floppy disk. It's a picture of a floppy disk. We don't use floppy disks anymore. And I have to say there was probably, when was it? Must be nearly 10 years ago now. I remember showing a floppy disk to a kid, young kid, and the kid saying, is that a 3D printout of the save icon? And I thought that was a moment, a sort of a watershed in history where, no, actually, it used to be an actual thing that you store data on. It is. This actual floppy disk is a thing you store data on. The save icon is a derivative of that sort of piece of history of computing that was the thing where you store data. But there are many other features of technology that are the effect of sort of history. I mean, there's some that are burnt in, like the width of a railway, the distance between the rails on a railway. That's something where it's burnt in because the infrastructure is built that way. It's very hard to change. But that's something that's sort of a historically determined thing, or the fact that I don't know if it's still the case, but I think you might still be able, Control Alt Delete. That's sort of an arbitrary thing that you press on Windows type computers to reboot them. That's again sort of a weird historical random accident that it is that way. And no doubt there are good things to do. These are comments that a floppy disk would be a good thing to 3D print. Yeah, you can really confuse people with that. You can give them the 3D printout and then say, do you have put it in your antique computer, what's going to happen, and so on. I have to say, back at the, I'm reminded of the 30th anniversary of Mathematica a couple of years ago. We had a party, and somebody had made these this sort of thing with celebrating the first version of Mathematica, and there were edible floppy disks. So these were, so that was another sort of cognitively difficult thing is, you know what a floppy disk is. You have this thing, it looks like a floppy disk, and actually you eat it and it has icing on it and so on. So that's kind of a weird thing. Oh, I see. The idea is floppy contains a 3D rendering of a printout of the floppy. Yeah. Well, look, there are really strange things. Like, for example, the first computer that I used back in 1972 used paper tape as its way of storing information. And we're about to make a virtual machine recreation of that computer, the Elliott 903, a very obscure kind of computer. And somebody was asking me, okay, if we make this recreation of the software, how are you going to read in your paper tape? And I realized the obvious way to read in the paper tape is to just, unroll it, take a picture of it, and just use image processing to decide where all the holes are in the paper tape. I just have to mention one other thing, which I find kind of fun. Back in the day, when was this? Probably 1980-ish. There was a spacecraft sent, the Voyager spacecraft, which is now the furthest away human artifact that is still in communication, I think, with us. I think the Pioneer spacecraft are further away, but they're no longer in communication. But the Voyager spacecraft is sort of the furthest away human artifact. But I think it was Carl Sagan was tasked with put something on that spacecraft so that if the aliens find it, they'll be able to decode features of human civilization. So famously, there was this kind of this golden record that was a circular disc-shaped thing, and it contained all kinds of interesting diagrams and all that kind of thing. And the idea was that this was a record, like a vinyl record. And so how does a vinyl record work? Well, for those who don't know, I mean, it's a thing for playing sound. It's the long predecessor of the MP3, and the predecessor of the CD, and so on. And the idea was that you have this thing, and it rotates. It's made of plastic. It has this groove in the plastic. It's a spiral groove. And what happens is there's a head that is a little tiny needle that kind of rides in that spiral groove. And as the thing turns around, it's kind of being moved from the outside to the inside of the spiral groove. And the whole point is that in the spiral groove, it's not flat at the bottom of this kind of valley that is the spiral groove, that it goes up and down. And as it goes up and down, that changes the pressure on the needle at the tip of this sort of head that's riding on the groove. And as that pressure changes, you can convert that into sound. And so you can play your favorite music, for example, that way. And so certainly when I was a kid, that was the way that one had music that had been recorded, was with these vinyl records, and they would rotate around. And there were, there were the 33, am I remembering right? The 33 revolutions per minute, and there were 60, gosh, I'm forgetting all this stuff. There were different standards for, depending on whether a big long playing record or a smaller one, different standards for for how fast the record would go around and so on. Because if you made the record go around at double speed, you'd be playing the music at double speed, and all the frequencies would be double the frequencies. You'd be going up an octave in the music, so to speak. But anyway, so back in 1980, everybody knew about vinyl records, and everybody knew how you would play a vinyl record. And it seemed kind of obvious. You have these grooves, and you have this thing, and it's moving around. And so Carl Sagan was like, well, if the extraterrestrials find this, they'll realize it's a record, and they'll be able to play it. And they recorded on that record sort of all kinds of sounds from Earth, of music and different human languages and all kinds of things. And it's got a lot of data on it of that kind. Okay, so, and they actually had this diagram, which is kind of like the instruction diagram of how to play this record, with a sort of picture of what the head looks like, and it's kind of a spiral thing, and so on and so on and so on. Okay, so now we're 40-something years later, and it's like, that's a really goofy thing, because it's like a record, a vinyl-like record. Who would ever think of doing that? That's really old technology. And so, for example, if we picked up that record today, what would we actually do with it? Well, probably what we do is we get high-resolution imagery that basically picks out the depth of that channel at every point in the spiral channel, and we'd then just do image processing, and we'd figure out, and we'd have to do this nasty, awkward piece of image processing where we unroll the spiral, and we'd say, gosh, it's a big nuisance they put the thing in a spiral. Why didn't they just put it in scan lines, rectangularly along the page? But we unroll the spiral, and then we can finally listen to that music. But so it's interesting in just 40 years how that kind of the evolution of technology has taken us to the point where what seemed like obvious, very robust technology of, oh, everybody would know how to play a vinyl-like record has transitioned into something that is really quite obscure. And of course, CDs, for example, worked differently. They didn't have a spiral groove. They worked with concentric rings and so on, and the different setup. And so it's sort of interesting to see how that works, and to see that particular technology of spiral grooves, I don't think has really been, that there isn't a, that has, I think, pretty much died out. But other things are still being sort of grandfathered forward because, it's too difficult to change or whatever else. Okay, well, I think I should probably wrap up here. Gosh, I left so many interesting questions here. Yeah, lots of interesting questions. Well, I look forward to addressing a bunch of these next time. So I should, oh, that's an interesting one from William here. I'm going to try and address that next time. Okay, well, thanks for joining us, and same time next week. Bye until then.